Alright, so the topic of this lecture is called Integral Action and PID Control. If we begin, or if we recap where we left off in the past lectures, you'll remember that we have a state space system of this form, and when we first began considering control of this system, we were trying to stabilize our state space system, or state x, and we used a control of this form, u equals minus kx, and the effect of this was to stabilize our system if we chose a good k, such that the eigenvalues of our system, or the real parts of them, were all negative. This led to a plot that, like you see here, where the initial state x is driven eventually to 0. After that, we considered a second type of control called reference control, or reference tracking control. And in this kind of control, you'll remember that we added to our stabilizing controller this gain times our desired output, ZD. And the result of this, in terms of our output, would be to go from some sort of initial output up and converging upon the desired solution. We also found in the prior lecture that if our system is a second order form system, meaning that it's of this form, and then we could use requirements such as the maximum overshoot, peak time, rise time, steady state time, or settling time, to compute our desired damping and natural frequencies, and as a result we can choose the desired gains that would give us K. And that's great. However, in practice, there tends to be one problem, and that is that if you have a state space system like this, in practice, you will need to make this state space system a model of your real system. Like that. So for example, if I have some sort of robot better robot. we will produce a model of this robot that'll include friction forces and torque from motors and its effect on the wheels and so on. If there's any error in that model and we apply our reference tracking controller to that and we plot the output of the system, over time, we'll find that the system converges to a steady state that's different than our desired state, and we call this steady state error. And to see why that happens, if you look back and assume that our the stabilizing control, or the stabilizing part of our reference tracking controller, stabilizes the real system as well as the modeled system, we can only apply the modeled H, J, A, and B matrices in the reference tracking control. And because that is different than our real A, B, H, and J matrices, there's going to be a difference in this input. And that's going to result, because this is constant over time, in a steady state error. Right. Okay, so the objective of a new form of control, which is the most commonly used form of control, that we'll call integral action, and for second order systems called PID control, is to incorporate a new term into our reference tracking controller. And in particular, we're going to introduce a new term into our system called EZ, which is the error between our output and our desired output. Or I should say, the time derivative of this EZ is equal to the difference between the output and the desired output. If we were to go then and reform our state space system, we can create a new state based on x dot and ez dot. And this will be defined as the difference between z and zd and a x plus bu, which we had before. Remember that z is defined as hx plus ju, so if we go and plug that in, we'll have a and h. Plus b and j plus 0 minus 1 times zd. Notice that what EZ actually is then is the sum of the error between our output and our desired output over time. And this is why we call this integral action. And if we wished to control our new system, what we could do is introduce a stabilizing controller plus a new reference tracking control, which we'll call KR, which could be the same as this gain in the reference tracking controller, but it does not have to be, and we'll see why in a second. If I went and expanded this a bit, this will make U equal to K minus KI EZ plus KR EZ. So this is the stabilizing controller. And this is the reference tracking. Gain. And this is our new integral gain. And this integral gain is called that because it's multiplied by the integral of the error between our output and desired output. Okay. To make this more explicit then, in practice and implementing this, we would still take our standardized control, but we would have to have in our code some sort of running integrator that would take our modeled output and subtract that from our constant desired output. And if I chose KR to be the same as the reference tracking controller gain, I would simply say that it is equal to this. Okay, where this term is KR, and these parts right here have to be modeled parts of the state space, which, remember, was the cause of the steady state error originally. So we're hypothesizing that this longer controller is going to get rid of steady state error by virtue of this term. Okay. We'll prove this by taking one simplifying assumption, just to simplify the math a bit, and we'll assume that J, remember J is a component of our output, Jm, is equal to 0. When we do that in our state space system, we'll have this form. And we'll therefore consider the evaluation of the extended state space system with our integral term. To look like that. If we apply our controller up here, so the control that we apply will be minus kx minus ki ez plus kr d. And I substitute that in for you in my new system. I will get ax minus bk x minus bki z plus bkr zd, and here I'll get x, or hx minus jkx minus bki z plus jkr zd minus zd. And remember that j in this particular case is 0. So, as a result, we will simply have minus zd, and remember that it's 0 over here too. So we will simplify it down to hx minus bkiez minus, jkiez minus zd. Again, j is 0 here too. And so that just becomes h of x minus zd. You can simplify this by collecting all the terms. So I get a minus bk, and here I get h, and here I get minus bk I, and here I get 0, and then I multiply that by my new extended state. So if I have a minus bk, that's a minus bk times x, and if I have minus bki times ez, that's equal to b minus ki times ez, and then down here I just have h times x, which is why that's there, and this is 0 because everything disappeared in terms of ez there. And over here I'll have bkr and minus the identity matrix times zd. Okay? And that's equal to this guy. This is just a standard state space system. And so the objective of designing a control with integral action is to take this matrix, which we will call our closed loop matrix. We call it closed loop because we're applying feedback to make our system stable. If this new system, or new matrix, has eigenvalues with real parts less than 0, just make this more clear. So every eigenvalue has real parts less than 0. Then this system is stable over time. Which also, by the way, means that this system is stable over time. This error is 0 over time. If the error of the system is 0 over time, even if it doesn't go to 0, if it goes to a constant, then what has to happen is the difference between our state, or our output, and our desired output must go to 0. Why? Because recall that ez dot is equal to the difference between our output and desired output. If this goes to a constant, then the derivative of this over time must go to 0. And so, as a result, if we stabilize this, and then our steady state error goes to 0. The implication of that is that if we have a difference between our model and our real system, then even if we have that error, applying an integral term in our controller will make this system eventually converge on the steady state error. If I go and introduce a disturbance system. Let's start with the normal steady state, or state space system. Okay, so this new term is a disturbance. It's like an input. But we can't tell the disturbance what it will be. We'd like our system to reach a desired output over time, despite this disturbance, and our integral term will help us do that. And that's because if we went and reform the state space system in terms of this integral term, if this disturbance is constant over time, just like ZD is, it becomes like an input. If this system is stable, even with the disturbance, then using the same logic up here, if the real values of the system are less than 0, then our integrated error term has to converge at least upon a constant, which means that because the time derivative is equal to the difference between our output and desired output, that difference must converge to 0. So despite a disturbance, which shows up here, our system will still converge to 0, or to steady state of 0 over time. So here, this just means that the output, as time goes to infinity, equals 0. Or the difference between the output and the desired output over infinity time. Notice that in this particular case, this is true despite the choice of KR. So KR, if chosen well, like this, might help us achieve better performance, but it's not necessary in order for us to have a desired state that goes to 0. Okay. Let's consider a variant of this integral control strategy called PID control. And in order to do this, we will assume that our system is a second order system like we talked about last week. So it will look like that. Our state space form for this system will have this A matrix, which is a function of the natural frequency and the damping term. And this B matrix. And remember, if our system doesn't fit perfectly within this, we can simply redefine U in order for that to be true. And we'll consider a Z in this case. That is just X. If we assume, just for simplicity for a moment, that we want a desired output to go to 0, then applying the integral action controller that we discussed before to this system, then we will get a minus kx minus ki e z. And this is because ZD is equal to 0 in this case. this means that we can separate this into a Kp times our state minus a Kd times our state dotted minus Ki times the integral of our state over time. These two terms are an expansion of this, and this is just an expression of our integral term when Zd is equal to 0. We call this the proportional gain, and we call this the derivative gain, and we call this the integral gain. Thus, P I D. That's why it's called PID control. And so this PID controller is just a case of the integral controller that we discussed before. And remember, this assumption is just a simplification, because we could have chosen alternatively Kr equals 0 to get the same result. And this is by far one of the most popular kinds of control used in industry, and so you'll see this pop up again and again in practice, and it's incredibly useful. So let's consider, before we end here, an example. And this is an example of a 2D satellite which has a state space that looks like this. So what does this mean? This means that if I have a satellite, looks like this, maybe it has some solar panels, I might define a coordinate system of the attitude of that satellite, described by an angle at which it points. This first line says that the difference in this angle over time is simply equal to the difference of the angle over time. That's just the identity, that's true. It says that the angular velocity of this system over time is equal to 1 over tau. In other words, it's a function of the torque divided by the moment of inertia of this system, and that's fine. We have this extra term added as a disturbance. You can imagine this is a disturbance torque. And we care about achieving some sort of desired orientation for time. So if we assume that we have a theta that's equal to 0 at time 0 and a theta dot that's equal to 0 at time 0, we might have a desired output that's equal to 1. In other words, we want our system to go from here to 1 radian or 1 degree, depending on what we choose. We choose 1 degree if we want. Then, according to the integrator dynamics that we were considering before, our state space system can be rewritten so that we add the easy state to our system. all this will do in terms of the state space will be to add an extra row here and an extra column. And because as we write this, we're actually including the controller, a portion at least of the controller, we're skipping it immediately to the state space form up here, right here. So D matrix looks like this with tau and ZD, and the disturbance looks like this. Implementing or finishing the implementation of our controller by changing tau to be a PID controller, we will end up with a system that looks like this. Recall that this torque only comes into play on this row of the state space system, this middle row. So the top row of our A matrix will still have 0, 1, 0. The middle row will become minus Kp times, divided by J, minus Kd over J, minus K I over J, 1, 0, 0. This is going to be followed by theta, theta dot, and easy. Over here we might choose to include now our reference gain. And we'll have our disturbance. You can see this plotted in my notes under lecture 17. But if I were to assume that J is equal to 100 and Kp is equal to 1000, Kd is equal to 1000 as well, and Ki is equal to 100. If I chose Kr equal to minus 10, and even W I could choose to be equal to 10 as a specific case. Notice a few things. First of all, I chose Kp, Kd, and Ki such that this matrix here had eigenvalues with negative real parts. So if the system would be stable, and my steady state will go to 0. This reference tracking gain does not or would not match the reference tracking gain that we initially started with up here in reference tracking control. But it doesn't matter. The system will be stable regardless. That doesn't mean that this is a good choice of reference tracking gain, or that applying the reference tracking controller gain that we derived before wouldn't be better. It probably would. But it's not necessary in order to stabilize the system. Moreover, even with this constant disturbance term, this system will end up being stable. The result ends up looking something like this. Remember, our desired output was 1 over time, and we started at 0. This system shoots up very quickly, and then it converges to the steady state. And that's that. And that's PID control and integral action in a nutshell. Summarizing, the integral control, or I should say integral action controller, begins by defining a term easy such that the time derivative of easy is equal to the difference between our output and desired output. And our input then is a chosen gain k times our state x minus our integral gain times ez plus a kr that we choose times our desired result. If we want this system to be stable, then we want the matrix this matrix to have eigenvalues with negative real parts and we assume here that j is equal to 0. And you can derive this new matrix for j not equal to 0 too, but this has simplified the math a little bit. And it's very common for j equal to 0. If we wanted to implement PID control, and then our controller is just a proportional gain times our state minus the derivative gain times the time derivative of the state minus the integral gain times the integral of our state. Assuming in this particular case that our desired output is equal to 0 and is also equal to the state as opposed to the derivative of the state. What we haven't talked about today is how to go and take our strategy that we used for reference tracking, which told us how to choose gains for k and for kr based on a second order system. Remember, this was the part where I talked about overshoot and rise time and use that to develop desired eigenvalues. We haven't talked yet about how to go and choose our new gains in the context of an integral gain. And this is often called PID tuning. And this will be the topic of our next lecture.